Hi everyone. Today we are going to finish up Chapter 2, Section 2, 2.2 by looking at local minimum, local maximum, and then finally even and odd functions. Okay, so to start off, we'll take a look at, and we're at 2.2 still, local maximum and local minimum. Taking a look at what these mean. So a local maximum or a local minimum, if we just wanted to describe it in plain terms, means the highest or lowest point in a certain part of the graph. So looking at a specific part of the graph, that's where the local comes from. So we're just looking locally within a certain area. The highest or lowest is where we see the maximum or the minimum point. Let's take a look at an example. We'll use these, or this quick description for this example, and then we'll go over our formal definition that our textbook gives us. Let's say we have the graph, or a graph that looks like this. Okay, so as you can see, we have some points where we switch directions, talking about increasing, decreasing, and constant, like we learned in our last video. These points where we end up switching directions are what we call local minimum or a local maximum. So let's take a look, for example, over here on the left. As you can see, we are going down and then we go up. So our point here at the very bottom of this curve, this is a local minimum. And again, we're just looking at a certain area of the graph. So let's just look maybe at this area of the graph. Within a certain area of the graph, it's a local minimum, we'll say for that interval. So when we define a local minimum, local maximum, we'll also sometimes talk about the interval that we're talking about, or the area of the graph. Then we go up. Eventually we get to a high point over here. We go up and then we go down. So this over here is one of our local maximum points. Local maximum. And again, we can just talk about an interval from here to here. And then one more local minimum we have down here. So as you can see, we go down and then back up. We have another local minimum. And again, that's a local minimum for a certain interval. We could define the interval really close. We could also define the interval really far away too. We could define a larger interval. If we look at this entire interval, this is our lowest point on the entire graph that we can see. Okay, so one thing to note is so notice that our local minimum on the right is actually less than our local minimum on the left. And that is okay. This local minimum happens to be our lowest point for the entire graph. But because we're only looking at certain parts of the graph, we also call this a local minimum as long as we look in an area that doesn't include that other minimum. So this is where the local or the part of the graph comes into play. All right, so this is how we can kind of identify or see local minimum and local maximum points. Right now I want to clarify the plural. You might see this, the plural for maximum is maxima. Maxima. And then the plural for minimum is minima. So we just kind of replace that end part. So when I say maxima or minima, I'm just talking about more than one minimum or maximum point. Here we have two local minima on our graph. Okay, so now let's take a look at our definition from our book. So our book is looking at formally defining it by looking at an interval again. So we start with a function f. F has a local maximum at C. Local maximum at C. If there is an open interval I. So again, just looking at interval I containing C. So C has to be within that interval, that area of the graph. So that for all x and for all, you might see for all written as this symbol too. That. So for all x that is not equal to C, so any other x value in that interval in I, the output for that x, so any other x, that output has to be less than the output that we get at that x value at that C point, basically. And then we call that output f of C a local maximum of f. Okay, so let's break this apart a little bit and see what these different parts of the definition mean. So a function f has a local maximum at C if there's an open interval containing C, so that for any other x in that interval, the output is going to be lower. For example, looking at a different graph. Let's look at a parabola. Like that. Okay, so here's our graph. We have a parabola, downward facing parabola. And then let's define our interval I. Let's just define it from here to here. The x-intercepts. So this is our interval I. And again, we're defining our open interval I, so some area of the graph. And here we can see that there's a local maximum at the point, at this point in our graph. Right here we have a local maximum. Okay, so this point we would call C. Here we have f of C. And our definition is saying that this is a local maximum, and we can say it's a local maximum because if we choose any x, and we can't choose C, so any x other than C. For example, let's choose an x here, x, and this has to work for all of the x's in the interval. And we take a look at the output. So here we have an output for x, f of x. You'll notice that the output for x is lower than the output for C. So because the output for any x, and that's true for any x that we choose along this curve, is going to be lower than C because that's true. F of x is always in this interval lower than C. Implies that we have a local maximum at C, or you could also say that f of C is a local maximum of our function f. Okay, so really quickly, an actual example. Let's take a look at the function again. Let's look at a downward parabola. Let's look at the function f of x is equal to x minus 2 times x minus, let's do 4. Okay, so here we have x-intercepts of 2 and 4. And the vertex, which happens to be our local maximum, is going to be up here. Our vertex is at 3, 1. Here we have 1, here we have 3, and this is our local maximum. So we have a local max at 3. In other words, 1 is our local maximum for f in this area. And it's the local maximum because if we choose any other x value, if we choose 2, then we end up with an output of 0. So if x equals 2, f of 2 equals 0, and f of 2 is less than f of 3. In other words, 0 is less than 1. So for any x value that we choose, we're going to end up with some output value that's always less than the output we get at 3. So in this case, c, the c value is 3 for our function. All right, so that's local maximum. Local minimum is very similar. We just switch a couple of things around. So for local minimum, I'm just going to go back to our definition. We use very similar wording. We say local minimum at C. If, same thing, we're looking at an area of the graph, we're looking at C, we're looking at all of the x values in that area. We want to make sure that all of the x values are greater than f of C. We don't have a ton of space here, but let's say this is our local minimum, f of C. We want to make sure that any other x value is greater than that. So any other f of x value is going to be greater than f of C. So that just means we switch around this inequality. And then it's a local minimum of f. Okay, so that is our formal definition kind of broken up. And again, it matches the kind of like plain definition that we went over originally. All right, next up, we're going to take a look at the even and odd functions. And we're going to start off by talking about symmetry. All right, so we're going to start by talking briefly about symmetry. So symmetry is just looking at things kind of like matching up on the graph. You can think of a mirror when you think about symmetry. And we can talk about symmetry across certain lines, symmetry across the y-axis. Means that we can take our graph, we can reflect it or flip it over the y-axis, and we'll get an exact copy, or it'll line up with the other side. An example of this would be if we had a parabola, y equals x squared. We could take the entire left side here, flip it over the y-axis, and then it'll match up with the graph on this side. So taking this side, flipping it, it'll match up with that right side of the graph. In other words, it's a mirror image from left to right, or right to left. So that's symmetry, it's matching up. We can also talk about symmetry over the x-axis, very similar. In this case, we're just flipping it over, we're flipping it vertically over the horizontal x-axis. An example here would be y equals plus or minus square root of x. So we have a sideways parabola. We could take this part, flip it over, and it'll match up exactly with that top part. And again, this is across the x-axis. Okay, so that's a little bit about symmetry. We're going to use symmetry to help us when we talk about even and odd functions. So even and odd functions have certain symmetries, and even and odd functions are helpful because when we have an even or odd function, anything that we know about part of the graph, for example, the left part of the graph, if it has symmetry across the y-axis, we can also apply that to everything on the right side of the graph. So let's start off. Even functions are functions where we see symmetry across the y-axis. So one way to identify even functions is to see if there's symmetry across the y-axis. Let's go back to, we have y equals x squared. We saw our graph was a parabola. Because there's symmetry across the y-axis, we have, in this case, an even function. So y equals x squared is even. So graphically, we can identify even functions by looking at that symmetry. We can also define it using algebra, or using the equation that we're given. And specifically, a function is even if for all x values in its domain, the output of any x value is equal to the output of the negative of that x value. So if this is true for all x values in the domain, then we have an even function. And we can see this with y equals x squared. If we look at f of 4, well, f of 4 is 4 squared, which is 16. And we can see f of 4 is equal to f of negative 4. And that's because the negative, when we square it, it becomes a positive number. In other words, if this is 416, if we reflect it and look at the negative 4, we'll get the exact same output. Odd functions are kind of like even functions, but there's one more step with the symmetry. Odd functions. Odd functions have symmetry across both the x-axis and y-axis. So both axes it has symmetry, which means we have to flip it twice and see if it matches up. An example of an odd function would be y equals x cubed, or f of x equals x cubed. We use function notation. So here, if we graph this function, we end up with a graph that looks like this. Kind of a curvy graph. And what we're looking for is, can we reflect this across the x-axis or the y-axis? Doesn't matter which one we do first, as long as we do both. Can we reflect this across the y-axis and then reflect it across the x-axis and match it up exactly? If we reflect it across the y-axis, this part is now mirrored. So it looks like this. And then if we take that and flip it across the x-axis, it does in fact match up with this right side of the graph, this top right at quadrant 1. So this is an odd function. We can see that by looking at the graph. We can verify this by using the equation to help us out, like we did with even functions. A function is even, or sorry, a function is odd if for all x in the function's domain, f of negative x is equal to negative f of x. So this is what we're looking for. F of negative x, so if we plug in the negative value of x, that should be equal to the negative output that we get for that x. And we can see this by trying out a specific value for x cubed. We can also see this by looking at x cubed as an equation, and that can verify it for all of the f of x equals x cubed. So f of negative x, well, f of x is x cubed, so if we plug in negative x, we have negative x cubed. Negative x cubed is going to give us negative x cubed, so because we're cubing, we still have a negative value. If we take f of x and make it negative, then we end up with negative f of x is just x cubed. So we end up with that same value, negative x cubed. You can also try this with individual values. If we were to plug in 2, negative f of 2 is negative 8. F of negative 2 is negative 2 cubed, which is also equal to negative 8. So here we can check for a certain value. This work that we did here proves that f of x, in this case, is odd, and it proves it for all x values because we kept the equation. So one note, when we looked at even functions, we tried out an example. We checked to see that this was even. If we wanted to prove this was even, we would have to use this equation, and we would have to plug in the original equation, y equals x squared, or f of x equals x squared. So we're checking x squared. Does that equal f of negative x? Well, f of x is x squared, so we take negative x squared, and we do in fact see that x squared equals x squared. So here we checked and we proved that y equals x squared is even. Okay, so for even functions, we're just looking for symmetry across the y-axis. For odd functions, we're flipping across both axes, checking for symmetry, and we can use these equations to prove that a function is even or odd.